Hello and welcome to another video. Today we are going to be talking through acids and bases for the AS level, specifically following from the OCR-A textbook, although this will apply to most exam boards for the AS level. So we're going to be talking through acids and bases. Now we're going to be talking about the Bronsted-Lowry definition of acids and bases, where acids are proton donors, e.g. HCl, where we get HCl when it dissolves in solution, splitting up into H+ ions and Cl- ions. So that HCl is donating the protons. Now bases, we can think of as the opposites of acids. So bases are proton acceptors, therefore. So this is something like sodium hydroxide, where the sodium hydroxide can gain a proton, and the OH- specifically gains the proton to form water. So all alkalis are bases, but not all bases are alkalis. You'll see in the textbook lots of times bases being referred to as alkalis or sometimes just bases. Now, the difference between these two is that alkalis are water-soluble bases. So if you see something that has the AQ symbol and it's basic, then that means that it can be called an alkali. But if you have something that is acting as a base that is solid, for example, then you can't call it a alkali. It's just a base. So acids and bases can be strong or they can be weak. Now, what does this mean, strong and weak? So strong means that the acids or bases can fully dissociate in solution, whereas the weak acids and bases only partially dissociate in solution. So next we'll see examples of what that partial or full dissociation looks like. So the example we've already seen of a strong acid was HCl, but I'm going to show you what a diprotic acid looks like in this case. So a diprotic acid that is strong, such as sulfuric acid here, when dissolved in water, for example. In fact, we'll put the water over the arrow. We get full dissociation of the acid into 2 protons and the sulfate ion. Now, this is called a diprotic acid, as you can imagine, because it forms 2 protons. It's got 2 protons to give away. The HCl that we saw was a monoprotic acid. You can also get triprotic acids, such as phosphoric acid, or you can get even greater numbers of acids, number of protons being given off by the acid, mainly for like organic species, where you can get several carboxylic acid functional groups. So this would be an example of a tetraprotic acid. But you won't see anything greater than a diprotic acid for the AS level. The phosphoric acid is just the extra there, the triprotic example. So this was an example of the strong acid. Then a weak acid would be something like one of our organic acids. So to keep it simple, we'll look at ethanoic acid. And here, as the name suggests, obviously it is an acid, but we are dissolving in water here, and we are going to get partial dissociation of this carboxylic acid. And so this isn't actually a full reaction like it was with the sulfuric acid. Here we form the ethanoic acid now in aqueous solution. It's now dissolved, but we have to have an equilibrium arrow for this to show that we go back and forth in this dissociation. So we can dissociate to form the ethanoate and the proton. So this behaves just like a normal equilibrium, and you see in more detail next year for the A-level how we actually calculate the pH of a weak acid. So we can basically tell how much this is dissociated and therefore determine what the pH of the solution is from that. So strong bases, just like strong acids, fully dissociate in solution. And we saw the example before of sodium hydroxide. When aqueous can fully dissociate to form Na plus and OH minus. Now, weak bases are a little bit trickier because they don't directly dissociate to form the OH minus like with a strong base. Instead, we get a reaction with water to form the OH minus instead. So a weak base would be something like ammonia. So ammonia has a lone pair of electrons on the nitrogen that can take a proton from something, either just take a proton from solution or actually react with water to get a proton from water. Now, ammonia isn't a strong enough base to actually take protons from water wholly, like it doesn't happen fully. And so this should be a equilibrium arrow as well. And the ammonia takes a proton from water to form ammonium, so NH4 plus and OH minus. And because this doesn't happen fully, we don't get 100% of the ammonia going on to form OH minus ions like we do with the sodium hydroxide. Instead, we're left with a mixture of the OH minus and the ammonia itself. So acids and bases can react together to form neutral salts. If we look at the actual acidic and basic parts of our acids and base, then we have our H plus plus our OH minus going to form H2O, which will be neutral. Now, our counterparts to the H plus and the OH minus, so for example, if we were reacting HCl and we were reacting sodium hydroxide, our Cl minus and our Na plus go on to form NaCl. So if we had our full reaction of NaCl if we had our full reaction of HCl plus NaOH, we would react to form NaCl and water. And I'm writing water as a liquid because that is the media that we've dissolved in. That is the solvent. So it's easy to form these full reaction schemes from the ionic equations because you just combine what's on the left-hand side and combine what's on the right-hand side to make the full equation. So any salt that forms, so here we have NaCl, which is just table salt. Any of the counterparts, so the sodium and the chlorine, but this could very well easily be calcium and sulfate, for example. Any combination of the metal and the anion here form a salt. And it doesn't matter if it's not table salt, it's still called a salt. So these salts are always neutral, and we always form a salt with any acid-base reaction. It doesn't matter what the base is, because we're going to see next that we sometimes have different bases. We always form a salt with these. So the first reaction that we're going to see is when we have a metal hydroxide and an acid. We've effectively already seen that because it's the same as the sodium hydroxide. I'm just going to give another example. So this time we're going to look at potassium hydroxide. So when we have a metal hydroxide and we react it with an acid, as a general formula, we get a salt and we get water. So let's look at that with potassium hydroxide reacting with nitric acid. So when potassium hydroxide reacts with nitric acid, the OH- and the H+ react together to form water. And our salt that we form is the potassium and the nitrate together. So potassium nitrate. The ionic equation that is actually occurring, though, the things that are actually changing, is the OH- plus the H+. And we'll see that's the same for most of these. So the next reaction that we've got isn't actually a base reacting with an acid. It's just a metal reacting with an acid. So it's not gaining, nothing is gaining the protons here, so nothing is acting as a base. But we still have to learn it. So here we have a metal reacting with an acid. Now this still reacts to form a salt, and we also form hydrogen gas. So here we've got magnesium, and we are going to react it with HCl. So we form a salt. Now remember, magnesium is a group 2 metal, and so we're going to have 2 chlorides to counter the charge formed. So we form MgCl2 and we form H2 gas. So the magnesium gives up its electrons to form magnesium 2+. The electrons go to the H+, go to the protons, and we form H2. Now, the H2 that forms as a gas, we would have to prove that it's H2 being formed. And so you can collect this gas and you can ignite it with a lit splint. And when you do, you'll get what we call the squeaky pop test. So you will hear a squeaky pop because you have basically combusted the hydrogen. And when you do so, it obviously explodes and gives out a big pop when it does so. So the next reaction is a metal oxide reacting with an acid. When we do this, we just get a salt and water, just like with the metal hydroxide. So here we've got the example of zinc oxide reacting with 2 lots of HCl, because again, zinc is a group 2 metal. And we form zinc chloride and we form water. So the oxide, the O2-, would need 2 H's to go with it to form the water, whereas before the hydroxide only needed 1 H to cancel that charge and complete the water. If we look at the ionic equation that's happening here, this time the metal is actually taking part in the reaction, and so we can say that we've got zinc oxide reacting with 2H+, and the reason why we can say the metal is acting, actually reacting here, is because this is a solid that we put in. And so, because it's going from solid to aqueous, I'm going to say that we've got a reaction happening. Whereas before, the sodium and the chlorine, or chloride, I should say, were already in solution, and so were effectively just acting as spectator ions. So we've got our zinc oxide reacting with our 2H+, and this is forming zinc 2+ plus water. So the last reaction that we need to see for these metals is a metal carbonate, and we can have a metal carbonate react with an acid to again form a salt, form water, and form carbon dioxide. So in this example, we've got sodium carbonate reacting with 2 lots of HCl. Note that the sodium carbonate is solid as well. And we form 2 lots of our salt. We form water, and we form carbon dioxide. So this is another reaction where we produce a gas, so we would have to prove what gas we're producing. And so you could either put a lit splint into the carbon dioxide collected and you would extinguish the flame, or you can bubble the carbon dioxide through lime water and the lime water would turn cloudy. I'll put a link into a video showing the lime water turning cloudy, if you just find it somewhere on the screen now, if you want to see that reaction. So the metal carbonate that we had obviously had carbon in it. And so when we react the carbonate with the H plus and we form the water, you'll see if you cancel out the 2 H's and an oxygen that we're left with CO2. So that's quite an easy way that I remember what we produce there. If we've got carbon in the base, we're going to have carbon dioxide form. So in the ionic equation for this, we've got sodium carbonate reacting with our 2H plus, and we're forming 2 lots of sodium plus, CO2, and H2O. So the last reaction that we need to look at is a reaction of ammonia with acids. So here we have ammonia reacting with an acid, and we produce an ammonium salt. And we also don't produce anything because the ammonium salt is the only product that we get. So here we've got ammonia reacting with any acid. So we'll say that it's reacting with nitric acid. And this produces ammonium nitrate. So NH4, NO3. So whenever you react ammonia with an acid, you always just produce the ammonium salt, whatever your acid may be. If you reacted it with hydrochloric acid, then you would produce ammonium chloride as your product. So I hope this was useful for going over some of the basics for acids and bases, what acids are, what bases are, some of the definitions, how acids and bases react together, and what products we form. Bear in mind that this year they're not going to give you any help when it comes to names. They're expecting you from names to be able to give symbols, and from symbols be able to give the names of things. So in the next video, I will go over the titrations. So how we actually work out the concentration of an acid or a base by reacting it with its counter. And we know the concentration of one of them, we don't know the concentration of the other, and we can use our moles equations to work out the concentration of the unknown from that. So I'll go over an example of the maths behind this, and also just an example setup of the titration apparatus as well, and some of the key bits you need when you need to know when you're designing an experiment for this. So thanks for watching, and I'll see you in the next video.